plus 2 dk minus 2. Can you see that dk minus 1 is 1 plus 2 dk minus 2? And I'm going to use it right now. The backwards feel very much like we call it, instead of calling it backwards, we could have called it Russian dolls. It feels like Russian dolls, one inside the other one, right there. So let me call it, this is the first time since 2009 that I'm going to call it Russian dolls. Right there. I just plugged in, and I'm running both at the same time. Right there. I'm running both at the same time. So I will do some chugging on this side. The chugging comes right now. I'll distribute. Right there. That was the chugging, only to distribute right there. Now, let me play on the left-hand side. On the left-hand side, I'm going to take a look at D3. Can you see how different they are? They are different. D3 is 1 plus 2. D2. Right there. And now I'm going to replace D2 by the one above. I'll say like this. All of you. That's going to be the plug. All of you is going to go there. All of you is going to go there. Right there. That's the plug. Right there. So on both places we did plug. Right there. Let me highlight the plug on the right-hand side. That was the plug. I replaced dk minus 1 by 1 plus dk2. 2 times dk2. So both are plugs. Let me call it plug. Plug. This one is also plug. Right there. Perfect. Now, let's do it again with the one. Well, let's plug in the one on the left-hand side. Right there. On the left-hand side will be D3. 1 plus 2. And then there is the actual plug. There. Of course, that 2 times 1, I know the 2 times 1 is 2, right there. But now, let's distribute. D3 is 1 plus 2 plus 2 squared. Right there. So we continue. On this side, we'll do dk. All of these are dk. 1 plus 2 plus 2 squared, and the plug right there. What is dk minus 2? dk minus 2 is a 1 plus a 2 dk minus 3. dk minus 2. Let me highlight it in green. dk minus 2 is 1 plus 2, 1 plus 2 times dk minus 3. Right there. And then I will chug. That was the plug. Right there. And I will proceed to chug. 1 plus 2 plus 2 squared, which I'm distributing, plus 2 cubed. Dk minus 3. Right there. So we're carrying both at the same time, and that's done sometimes. Some students get headache running both at the same time, and I will understand that right there. But they're both important because in other recursions, usually the one on the left fails and the one on the right continues. So the one on the right has been better on many situations where I need to compute recursions that they're more complicated and they come on the class, the computer science class, performance of algorithms. In the performance of algorithms class, the recursions are more spicy. And then the one on the right hand side will be stronger. It will continue. The one on the left will give you nothing, will give you a little information and then just dilute. Perfect. Right there. Let me find in the textbook. I'll bring you a page. I'll bring you to a page right away. That happens. We don't cover this section in the textbook right there, but I'll go to a page. I'll grab the page at once that happens. It's at the end of the textbook. Then I will continue with the recursion. Let me see. Yeah, it's in the analysis of algorithms and efficiency right there. So it's from the class. Okay. Page page 805. Page 805, they're using the left method, but the right method would have been better, the one on the right. Page 805. So perfect. Let me close that. That's not on the exam. Those perfect. 805. Page 805. I'll put it here. That's just to look at one that you'll see in your future if you are computer science. So for CS, look at page 805. Right there. Now, let's continue with our job right here. So the next one, I want to play with D4. D4 is 1 plus 2 times D3. Right there. But then we know what D3 is. D3 is all of this. And we proceed to plug. Right there. So then we're going to have D4. It's equal to 1 plus 2 times 1 plus 2 times 2 squared. And that was the plug. And now comes the chug, which is, in this case, nothing more than distribute. And the pattern is emerging. I'm adding powers of 2 right there. I'm adding powers of 2, and we know the formula for that. Let me play a little bit on the right hand side. The decay, it's equal to 1 plus 2 plus 2 squared plus 2 cubed times 1 plus 2, dk minus 4. Let me, there. Close. That was the plug. Right there. That was the plug. And now comes the chuck. Perfect. Right there. We're ready to finish it. We're ready to finish it. Let me do the analysis on the right-hand side, the one that was new, the one that was learned today. The one on the left, we learned that last class. The one on the right is new. Let me this is today. This is new. This is new today. Let me look at the analysis. So now I start talking to myself if I'm doing this for homework. I'm going to say this. This number is going to, I need a moment to think. This number is going to keep going down. K minus 5, K minus 6, K minus 7. So ultimately, it's going to go all the way to 1. This is going to go all the way to 1. That's the first element. Meaning, ultimately, you're going to get D1 right there. You're going to get to D1. Perfect. Right there. So, in being able to get to D1 right there, as it keeps going down, I'm going to get all the way to D1. Right there. How do I get to D1? I need the correct subscript. I will get to D1 at the moment that I get a K minus a K minus 1. Right there. That's the only way I can get to D1. That keeps going is K minus 4, K minus 5, K minus 6, all the way to K minus 1. Because what is K minus 1? K minus 1 is 1 right there. Okay, with that K minus 1 is 1. So at the time that goes all the way to 1, this one grows. That one grows. So this one goes down. There, that one goes down all the way to 1, the subscript. This one grows. The power grows. All the way to what? All the way to what? It's going to be a 4, a 5, a 6. All the way to which value?
K?
No K. But K minus 1. It grows all the way to K minus 1 right there. Can you see? On one of them, you're subtracting K minus 1. On the other one, you're adding K minus 1 all the way to K minus 1 power-wise. Okay with that? At the moment, so you're going to say, ultimately, this will happen. Right there. That's why I'm doing that analysis. This is not trivial. DK, ultimately, so that was the analysis done right there. I'll get the 1 or the 2 to the 0 plus the 2 plus the 2 squared. But I will go all the way to the last element. That is a 2 to the K minus 1 times D1 right there. Let me circle all of that. That's what happens ultimately right there. And what is D1 equal to?
1.
1 right there. So ultimately we get dk 1 plus 2 plus 2 squared all the way to 2 to the k minus 1 times 1 right there. And then we have a formula for that because we know that 1 plus 2 plus 2 squared plus all the way to 2 raised to the k is 2 raised to the k plus 1 minus 1 over 2 minus 1. So we have that formula right there. We have that formula right there. So let me check in what page in the textbook that formula is there. Let me see. 55756. It's on 57, page 345. That formula right there. So perfect. Now, let's play with the other side. Right there. Perfect. I can see that with the 3, I go all the way to 2 to the 2. With the 4, I go all the way to 2 to the 3. So I would have made a conjecture, a guess. Right there, that with the 5, I'm going to go all the way to 2 to the 4. It's a conjecture. And now I try it. And let me highlight. The conjecture was that claim right there. So I'll check it. I'll check. It is not induction. This is just to come up with a guess by the left hand side. So I would have said, okay, let's check. It's not the ultimate proof. So that's it. D5. It would have been 1 plus 2 D4 right there. But D4 is 1 plus 2 plus 2 squared plus 2 cubed. So then we proceed to, that was the plug. And then we chug. Which is in this case only distribute. And the answer is yes. Right there. Yes. So now we have a formula. We have a guess. right there. The guess is right there. The guess is dn is 2 to the n minus 1 over 2 minus 1, which is basically 2 to the n minus 1. Happiness with that. I'm using the formula, but our recursion goes all the way to k minus 1. So when you use the formula goes all the way to k to be able to get the k plus 1. Our recursion goes all the way to k minus 1. So if I'm going to utilize the formula, it's a 2 to the k minus 1 over 2 minus 1. Let me put that in green. Can you see what we did right there? So all of this is patterns by continue computing and doing those two, the Russian dolls and the forward method. Now we need to check by induction that this is the case. Proof by induction. So this is our guess right there. So the problem by induction will say, so check the correctness by induction. Let me make it thicker. Check for correctness of pattern by induction. Right there. So it will say this. The problem will say, show that the elements of the recursion satisfy. Let me put the recursion. The recursion is dk equal to 1 plus 2 times dk minus 1 for k greater than equal to 2 and k in C plus and d of 1 equals 1. So that's the recursion. Let me circle it. Show that the elements that come out of this sequence, of this recursive sequence, satisfy the explicit formula. The explicit formula. And the explicit formula is the nth notation. dn equals 2 to the n minus 1 for all n in C plus, right there. So this is math that I never did before till I was in discrete math. Okay, I didn't see this in calculus 1. I didn't see this in differential equation. I didn't see this in any other class before, right there. But they created a pre-calculus textbook that we use at ACC in the year 2001 to 2011 that play with this in the pre-calculus class. Okay, with that, they did recursion. So I had to do recursion in my pre-calculus class, meaning when I was teaching pre-calculus at ACC, but I never saw this anywhere else. That was a super crazy, spicy pre-calculus book right there that we got rid of, we don't have this in pre-calculus. I think it's too early to have recursion in pre-calculus right there. But believe me, I had to prepare for pre-calculus because they had this right there. Yeah, I mean, I had to work the problems out before going to class because I could get stuck. Okay with that? Okay, there. So this is, yeah. Perfect. Let's do the induction. But any questions on this? The mistake that I could have made, that it would have been the most popular mistake. What mistake I could have made that it would have been the most popular mistake? Even as I know what I'm doing, but I could have made a mistake. Which could have been? The k minus 1 is the queen of the problem. Okay, with that, the 2 raised to the k minus 1. That conclusion that I made right there, when I was doing the analysis, realizing there was no k, but k minus 1 was crucial. I could have called it k right there. And that would have, and of course, my induction would have told me that I made a mistake. So induction comes to the rescue to tell you you made a mistake in your pattern. Or it will tell you you are correct. I'm glad because that's not the case with every method. One method will work to tell you if you are correct, and the other, and the negation might be no information. Okay with that? So I'm glad that it works for both. It works to tell me that I'm wrong. So perfect, right there. So let's do the induction, right there. So here it comes. Is it traditional proof by induction? So now we'll go proof, right there. Let Pn be the predicate. Be the predicate. Elements of the recursion. Satisfy the formula to the n minus 1. Right there. So no quantifier. I didn't put the for all n in C++. So that means some elements could satisfy, some elements might not. So here it comes. Base step. Right there. Show P1 is true. P1 is true means that the output that comes from the recursion, which is 1, when you plug in for n1, you get 1. You also get 1 with the formula. So the recursion starts at 1. Comma, since d of 1 is 1. I'm sorry, when I'm saying starts at 1, it's confusing. That 1 is that 1. The recursive sequence starts at the output 1, right there. That's what we mean. Not the subscript, not the subscript. Comma. See that? Two raised to the 1 minus 1 is 1 right there. So yes, The recursion, the first element of the recursive definition is the same as when you plug in 1 for n in the formula. They're one and the same right there. Check. P1 is true. Yes. P1 holds. Perfect. Now, the inductive step. Show P of k implies P of k plus 1 is true for all k in C plus. Now is the algebra part. So we need to assume pk. So the ingredients right here is assume pk and write the recursion at the kth plus 1 element right there. Write the recursion at the kth plus 1 element. So the consider part, let me go all the way up here. For the consider part, I'll put it here. So I'll write it like this. For the consider portion, I'll write it in yellow. This is under induction. For the consider, you're going to have k plus 1. And here, k, because you are assuming k. And you'll be able to plug in for k and do all the algebra. So you are going to plug in for k right there. Happiness with that, right there. So that's going to be, that's the consider portion under induction. Consider, let me write that. Consider under induction. Perfect. We have that note right there. So perfect. Let's go all the way down. Perfect. So assume pk comma. That means that the kth element, that means that, oh, I don't know why an arrow showed up. Yeah. I don't want the arrow. Yeah. That means that the kth element of the recursion satisfies the formula. So dk, it's equal to 2 raised to the k minus 1. That's the assumption that we're making. The kth element of the sequence is dkth with the subscript. Satisfies the 2 to the k minus 1 right there. So now comes the consider part. Let me change to blue, to purple. Consider. And here comes the recursion. Consider d k plus 1 equal to 2, or 1 plus 2 dk, right there. 1 plus 2 dk. I'm going to put my pen in the case right there. But you know what comes next? Plug in for dk, the dk to the minus 1, and then do the algebra, because you need to end up with the 2 dk to the plus 1 minus 1. So we know what we have to end up with. I'll write it right away. I'll let you write the next move. I'm waiting for you to write the next move while I'm taking attendance. Okay, I'll write the next move. So the next move, we know what we want. We want, I put it right here at the bottom, dk plus 1 to be equal to 2 raised to the k plus 1 minus 1. That will mean that it moved forward. You continue with the same pattern. So here we come. We plug in. Right there. So that's the algebra that I need to show. And here comes the next one. Right there. So can you see how the twos are going to become 2 to the k plus 1? And the 1 and the minus 2 are going to cancel to give me that negative 1. Right there. So let me see. I'll bring that down for a second. Let me erase it. I'll do this algebra. And ultimately what we want. Right there. So yes, the pattern continue. K plus 1. The k plus 1 element of the recursion satisfies the formula right there. So we have a closed form. We have the time traveler. The time traveler is 2 raised to the k plus 1 minus 1. Or essentially this. The time traveler is dk 2 to the k minus 1. The explicit formula can travel across that recursive definition. The recursive definition is trapped in time, just like we are trapped in time. in that linear time that we have. But the explicit formula can go to the 10,000 element right there. Can you see what I'm saying? So here I can tell you. So let me write the conclusion. Thus, Pn holds for thus by PMI, by induction, thus by mathematical induction, Pn is true for all n in C+. Right there. So I'll close this. What have we shown? We have a recursion. With initial conditions. That initial condition. And we have an ordinary sequence. And this ordinary sequence can provide me any element in that recursive definition. For example, if I want to know the fourth element, I'll do a D4, and it will be a 2 raised to the 4 minus 1. Right there. And in that case, we'll have a 15. Right there. But again, if I would have gone here, if I do not know the closed formula, here, of course, I need both. To get to dk, to get to d4, I have to do the sequence. It's trapped in time. 1. Plug in the 1 to get a 3. Plug in the 3 to get a 7. And plug in the 7 to get a 15. And then I would have had to make all of those computations to get to the D4. Right there. So let me just mention this. We have the Fibonacci numbers. So Fibonacci is 1, 1, and sum up those two to get the next one. And sum up the previous two to get the next one. And so on. Right there. So we can write the Fibonacci's as a recursion. F of 1 is 1. F of 2 is 1. And f of k is f of k plus f of k minus 1. And this is for k greater than or equal to 3. Right there. Now, I want the 12th Fibonacci. That's it. If you want the 12 Fibonacci, right now you're going to have to go through the recursion because we do not have the formula for the Fibonacci's right there. That's the formula. Oh, go ahead. Question.
Yeah, Professor, I think the fk equals to fk minus 1 plus fk minus 2.
You got it. Let me fix it at once. Thank you. K minus 1 and k minus 2. Thank you for coming to the rescue. Perfect. Right there. So, we do not have the formula for the Fibonacci's, the closed formula. That's the formula that took 600 years. Right there. So we need to travel to the 12th element by continue. So it will be 1, 2, 3, 5, 8, 13, and so on to find the 12th. So far I have the 1, 2, 3, 4, 5, 6, 7th. This is the 7th element. Right now. Perfect. Okay, there. I want an explicit formula. Right there. So we will not get it. We will not get the explicit formula here, but I can tell you what it has in it. It has this number in it. In the formula, this number shows up. Okay with that? That number is irrational. So it has powers of irrational numbers, giving me, it has powers of irrational numbers, giving me integers right there. So super mysterious in math right there. Realize that when they came up with this formula, it was it really felt mysterious right there. But again, we don't cover section 5.8, and it's in section 5.8. But take a look at, let me see, section 5.8. Yeah, the formula is in section 5.8, and we don't cover that section. But again, we can solve these ones, the first order linear right there. So let me put it right here, section 5.8. Right there is the closed form. Okay. Next, let me take a look at one problem from section 5.6. I'll run to 5.6 right now. Okay. Problem 9. I'll go and grab it. Problem 9. I'll go and grab that problem. Let me see. There. 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 And then run to problem, let me see, bookshelf. And run to problem 9. Section 5.6. Right there. I'll put my pen in the case. So there, section 5.6 exercises. Problem 9. Perfect. Let me grab it. Oh, then we can click on the answer. But let me see. I got it right there. 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 Copy. And send it here. Okay. Look at this problem. A few years ago, maybe 2012, I was teaching this class at Northridge, 2010, 2012, and a colleague of mine was sitting in the class. So I looked at this problem really fast, and I started doing a proof by induction. And then I saw the face of my colleague. So then I realized I made a mistake because I look at human expressions. Okay, without that, I pay attention to human expressions. So I said to myself, I messed up. And that's it. Yes, I messed up. This is not a proof by induction because look, we didn't start with a recursive definition. We started with a regular sequence. This is the input. It's a regular sequence. It's not recursively defined. That is the time traveler. I started with that one. I didn't have to fight for any patterns. Can you see? They gave me the explicit formula. And they're asking me if the explicit formula satisfies the recursion. Is the other way around. Can you see? Is the inverse of the problem before. No induction, only plug in. It's a super easy problem. Okay, with that, this is called the no induction problem. I started doing induction because I do always induction. So I'm addicted to induction. So then when I saw the face of my colleague, I was like, no way, I committed the no induction mistake. So perfect, here it comes. This is no induction. Because it says, show that the ordinary sequence satisfies the recursion. So let me emphasize that. No induction problem. And let me say it here. For induction, the input is a recursion. A recursive sequence. The output it's an ordinary sequence. That we got by pattern. Right there. No induction. The no induction problem. The input is an ordinary sequence. And the output is a recursion. And now let me put the details. Let me put a fence. And the details. The one above says this. Show that the elements of the recursion the input satisfy the formula, the ordinary sequence. This, the ordinary sequence. The ordinary sequence is called the explicit formula, the time traveler. The one below says, show that the ordinary sequence, and I didn't put sequence right here, ordinary sequence, show that the ordinary sequence satisfies the recursion. Right there. And the ordinary sequence is the explicit formula. The closed form. The time traveler. The problem is very easy. Input the sequence and show that it works. Right here. So input the sequence. So grab, it's a super short problem. I'll do it in this space. No induction. I don't need to write sentences. It's a super cool problem in terms of saving time. Right there. It doesn't happen that often in applications because usually in computer science, you start with a recursion. You never end with a recursion. You start with a recursion. So, but this problem is, I have this one. Let me see. Right there. Oh, it's making these boxes that I do not want. There. Okay, perfect. It starts with AK. I'm going to plug in. So AK 3K plus 1. And I'm going to plug in that equation, 3K plus 1. Right there. There, 3K plus 1. Of course, I'm going to plug in AK minus 1. AK minus 1 is that. And I'm going to plug it in the recursion. So when I see the AK minus 1 plus 3, that is equal to 3K minus 1 plus 1 plus 3. And that is equal to 3K minus 3 plus 1 plus 3. The 3's cancel. And I end up with 3K plus 1. And 3K plus 1 is AK. And I'm done. Can you see what the problem is? Did I have to write a single sentence? No. It was all computational. Plug into that equation and show that by plugging in AK minus 1, you get to AK. Happiness with that. So it does. The ordinary sequence satisfies the recursion. No induction. No induction, not even complete sentences. I have the inputs. I have that. I know that should be the output. That should be the input. Put them in the recursion and show that they work. This is the input, is the AK minus 1. The output is the AK. Run them through the recursion and show that from AK minus 1, you get to AK by plugging in the formula right there. So no induction. And those are the problems in section 5-6. So let me emphasize that. It seems that when I learned this, to me, they seem the same, but they're not. They're very, very different. Induction is recursion, from recursion to a closed form. So let me put right here the problems. The set of problems there is 9, 10, 11, 12, 13, 14. That's it. 9, 10, 11, 12, 13, 14. Let me go up. 13, 14. Section 5, 6. Right there. Happiness with that? Perfect. Let me go and take a look at a problem in 5-7. So sections 5-6 and 5-7, they are twin sections. So let me say that. Section 5-6 and 5-7, they could be one section right there. So section 5-6. They are twins. Not identical twins. They just complement each other as siblings. Okay, with that right there, they were born at the same time, but they are not identical twins. But somebody could have written that as a one section. Somebody could have written one and only one section. But I'm glad Susana didn't do that, because on 5-6, we have the no induction. And on 5-7, we have the induction right there. Okay, happiness. Perfect. Let me go to 5-7. Find an explicit formula for. The recursion. So we're starting with the recursion. This is, I will have to do a proof by induction. Find the explicit formula for the recursion right there. And the recursion is BK equals to BK minus 1 over 1 plus BK minus 1 for K greater than equal to 1. And the initial condition is B naught is 1. So they start at 0. They start at 0. This is for K in the naturals. Right there. The first time I saw this recursion, I said to myself, that's super hard. That's really, really hard. That's super spicy. As soon as I saw that, but I'm sorry, it's not. It's really, really easy right there. But it gave me the feelings of super spicy. And that's math. Sometimes math with a very simple problem, it turns out that it's super spicy. And with a problem that might look spicy, is super easy. Happiness right there, it's just the mystery of math. And I just need to accept it right there. So let's try to play forward. Let's try to play forward. I don't need to play backwards on this one. So let's explore. So solution. Let's fight for a pattern. It's an intellectual fight, not an aggressive fight. So fight for pattern. That could be a really cool t-shirt that says fight for pattern. Yeah. A sweatshirt, a hoodie. Right there. Fight for pattern. Let's fight forward. Right there. So the one. B naught is 1. Right there. And let me plug it in. As soon as I plug in the 1 to be able to get B1, I get B1 as a 1 over 1 plus 1, which is a 1/2. Right there. Let's get B2. B2. B2 is a 1/2 over a 1 plus 1/2. But that is equal to, here's where it becomes easy. That is equal to a 1/2 over a 3/2. And that becomes a 1/3. Right there. And then I start seeing some sort of a pattern. A 1. It's a 2. Right there. The 2. It's a 3. Right there. Let's get the next one. We cannot sense it that the next one could be, let's check. B3. It's a 1/3 divided by let me write my fractions a little bit better so they don't look like divisibility. Right there. So it's a 1 over 3 over 1 plus 1/3. That's it. Let me check. Yeah, that's what it is. And then this is a 1/3 over a 4/3. And this is a 1 over 4. Right there. Happiness with that. Perfect. So we have a pattern. Let's make a conjecture. Let's make a conjecture really fast. Oh, it's almost freedom. So let me see. That's a 3. That's a 4. We make a conjecture. And then we still need to do induction. But the conjecture for the pattern, not proving that it will be this. It will be Bn. It's equal to 1 over n plus 1. Right there. It's one more. It's one more right there. So that's the conjecture right there. Remember what was our recursion? The recursion looked super spicy. It looked like a BK equal to a BK minus 1, 1 plus BK minus 1 for all K greater than equal to, there we got it, 1. K in the naturals, B of 0 equals to 1. So we have both. There is the recursion, there is the conjecture, and of course we can check one more step right there. And then super freedom, the B4 1 4 1 plus 1/4 1/4 over 5/4, and that's the 1/5 right there. So we need induction, but we end up with a potential closed form. So that's a potential. So it needs to go to the job interview. The job interview is induction. Any questions? Any questions? Super freedom. I kept talking for 2 minutes. Super ultra freedom. You have places to stay, to go, and do things. Any questions? Any questions? Enjoy the weekend.
Thank you. See you next week.
Bye.
See you next
Have a
week.
good